So we talked last class about different ways that you can make use of the pigeonhole principle. So this is more useful than you'd like to think. So the pigeonhole principle is really simple. If I have n plus 1 pigeons and I only have n pigeonholes, so I have more pigeons than I have pigeonholes, then no matter how I allow the pigeons to go back to their homes, at least one of those pigeonholes is going to have 2 or more pigeons in it. Okay? This is silly, right? That seems like the silliest thing ever. So at least one pigeonhole will have 2, possibly more, pigeons in it. Okay, that's the simplicity of this. And so then you might be saying, oh, Angela, what are you on about? This is a completely useless tool. Like, so what? How many times in my life have I ever put pigeons in pigeons' holes? How can you use that in really strange ways? And you can. So I can use the pigeonhole principle to tell you that without a doubt, there are 2 people at Dow that have the same exact initials. What does that have to do with pigeons and pigeonholes? At least 2 people at Dow have the exact same initials. So why does this matter? Okay, first of all, maybe it doesn't matter at Dow, but it would tell us that we can't use initials as any identifying factor because at least 2 people have it. Your student ID, that is unique. So it's really critical sometimes that we have unique identifiers. Initials, well, those are letters, right? How do I prove that there are 2 people that have the same initials? So, for instance, mine is AAS. I don't know that there's somebody at Dow that has my same initials, but I know that there are 2 people with the same initials. How would I go about using the pigeonhole principle to show that's true? Where would that even come from? Here's what I always do. I actually do this. If I want to apply the pigeonhole principle, what I need to do is the following. I need to think about, first to myself, is what are the pigeons and which are the pigeonholes in this scenario? As soon as you think about what am I trying to show there more of, these are the students. The pigeons, no offense, are the students. The pigeonholes are the initials, the possible initial combinations. Right? So AAA, AAB, etc., all the way through to Z, Z, Z. Those are the initial combos. Okay, so we want to show that there's more students than those combinations. And you can Google this, the number of students at Dow. It's changes, but I'll tell you this, it's greater than 19,000. I think it's 19,800 something this year. Okay, so how many combinations are there for initials? Well, in the first letter, I can put 26. And we'll get to counting later. The second letter, I can have 26. And that third letter, there are only 26 letters of the alphabet. So, or the English alphabet. So, does anybody know what 26 times 26 times 26 is? I wrote it down for myself so I don't have to do it again. 17,576. Okay? So, we can't use initials as a unique identifier for students because at least 2 people will overlap. But no matter what, we have more pigeons than we have pigeonholes. If you pick 5 cards from a normal deck of cards, pick 5 cards from the deck, then at least 2 will have the same suit. So which are the pigeons? Which are the pigeonholes? The suits specifically are the pigeonholes, and the cards are the pigeons. You can go ahead and prove it, but essentially you've got your 5 cards, and they have to map to one of 4 suits: hearts, diamonds, oh boy, can't draw, and spades. Right? And so no matter what I do, I can do pretty good for the first 4, but that 5th card is going to have to go to one of those suits. And that's the pigeonhole principle, is that I have more pigeons than I have pigeonholes. I have more cards than I have suits to map them to, then at least 2 of them overlap. Here's another simple example. Anybody ever wondered, like, find it troubling to find socks in a drawer? My son hates this. He doesn't like to find matches. He doesn't like to pair them up when he brings his laundry. He just wants to clean things and dump them in his drawer. He's 13. Anyway, so we solved that problem. And we solved it with the pigeonhole principle. He's got 2 colors of socks, 2 types of socks. He just dumps them in the drawer. And so I'll tell you, my son only has black and white socks. Only black and white socks. How many socks does he have to take to know that he has a pair? So the reason an even number of socks might not work is he could pull white and then he could pull black. Or he could pull black and then he could pull white. But as soon as he pulls that 3rd sock, it doesn't matter which he draws here. It's going to be white or black or white. He's going to get a match. It's either the whites or the blacks, but no matter what he does, he's going to get a match. Okay, so 3 is the magic number. So the other day, I suggested something that was just crazy. I tried to buy him, gasp, some gray socks. And he had none of it. They were on sale. They were nice quality. But he was like, no, I only have black and white socks. What if I had bought him those gray socks? Then how many does he have to draw in order to ensure that he has a pair? Because in this scenario, what are my pigeons? What are my pigeonholes? So socks and then the colors of the socks. You might have had the match in the first 3, so you only ever need that 4th. Okay, so sometimes the pigeonhole principle applies in more interesting ways. So I'm going to ask you this. How many numbers do you have to pick from the integers 1 to 8 to ensure that 2 of those that you've chosen add to 9? So you need a pair that add to 9. So how many do I have to choose? And here's the easy question. What are my pigeons? And then here's the harder question in this scenario. What are my pigeonholes? If they fall into the set 1, 8, they're going to add to 9. If they fall into the set 2, 7, they're going to add to 9. If they fall into the set 4, 5, they're going to add to 9. And so essentially we just need to figure out how many numbers we have to pick such that we have 2 landing in the same set. Is that right? So how many then, if those are pigeons and pigeonholes, how many numbers do I have to draw? I've got 4 pigeonholes, so I need 5 pigeons, right? I need to draw 5. Or pick 5 numbers. So you're either going to draw an 8 or a 1, or you could draw a 2 or a 7, or a 3 or a 6, or a 4 or a 5. Okay? So if I'm mapping the numbers, they're going to fall into one of those buckets, right? They're either 1, 8, 2, 7, 3, 6, or 4, 5. And as soon as I draw the second element from those buckets, now I've got something that adds to 9. Okay? So if I draw a 1, then a 2, then a 3, then a 4, so far I don't have anything that adds to 9. So I can easily draw 4 numbers that do not add to 9. But as soon as I draw the next one, it's going to have to fall into one of those buckets. And now I've got a pair that adds to 9. So it's that 5th number. It's going to be forced to have a match. So now let's think that we have a party with more than 2 people. 2 or more people. Sorry. 2 is okay. Then if we have a party with 2 or more people, at least 2 people, then at least 2 people at the party have the same number of friends. Why does this map to anything? What does that even mean? And how do we start this? Okay, so some of the time what we have to do is consider possibilities. So I'm going to give you a case, 2 cases. Case 1, everybody has at least 1 friend. And case 2, and then I want you to start thinking, what are my pigeons? What are my pigeonholes? Why is this a pigeonhole example in the first place? Someone has no friend. These are my 2 cases. What are the pigeons? And actually, I'm going to give you a hint that in both cases, the pigeons are the same. And in fact, technically, the pigeonholes are the same. So what are the pigeons? So they're the people at the party. How many are there? And that's a good hint. Well, let's say we have to start with something. So we'll assume n people. So that we're not putting a number on it, but we're actually just saying, you know what, assume there's n people. Then how do we split that up? So again, this is the people at the party. So we have n pigeons by assumption. What are my pigeonholes? Well, what am I trying to show I have duplicates of? If I didn't deal with cases at all, what are the options for the number of friends that somebody could have up here? Okay, so up here, what are my options for the number of friends? If there's n people, how many people could I be friends with at the party? So my number of friends, I could have no friends, right? Yeah, I could have 1 friend. I could have 2 friends in the group, and I could have all the way up to n minus 1. I mean, I like the idea of being friends with yourself, but, I don't know if we're going to count that. So I have n minus 1, 0 to n minus 1 friends. If those were my pigeonholes, how many options are there? That's n options. So the problem is if I have n people and I have n possible numbers of friends, and that's what I'm thinking is my pigeonhole, I've got a problem. Because now I've got myself in a situation where I do not have more pigeons than pigeonholes. I have the same number. And this is when cases come in very handy. Because now I just restricted the possible set of friends that one could have. If everybody has at least 1 friend, then what does this change to? I can't have 0 anymore, can I? 1, 2, all the way up to n minus 1 still. How many options is that? Now I don't have n anymore. I got rid of 1, right? 1 to n minus 1, that's only n minus 1 options. So now I've got n people at the party. I've got n minus 1 possible numbers of friends options that they could have. And so I know I've got more pigeons and pigeonholes. At least 2 people have the same number of friends. Done. And you don't have to show anything. You just say, by the pigeonhole principle. So what about when someone has no friend? Now, what are the pigeonholes that I can place them into? Sadly, somebody can have 0. Uh-oh. Now we have n numbers. Somebody, and here's the ticket. So it's very tempting to think it looks like this. And then we're stuck because that's n. Oh, sad. And that makes us sad because we can't apply the pigeonhole principle. But don't be sad for long, because what's true, can we actually have n minus 1? Yeah, friendship is mutual. If I'm not Brent's friend, Brent's not my friend. So he can only have between 0 and n minus 2 friends, which is great because I get to turn my frown upside down, don't I? Because now I have n minus 1 options. And so my proof is done because by the pigeonhole principle, I've got a possibility of n minus 1 friend group options, and I have n people at the party. So by the pigeonhole principle, 2 of them align. Okay. So if I'm at a party, I'm going to draw something out for you. With 6 people. So at a party with 6 people, there will be either 3 mutual friends or 3 mutual strangers. That means 3 people all know each other, or 3 people all don't know each other. Okay? So how on earth would anybody start with the pigeonhole principle in this one? And this is where things get interesting, right? Because you just start with one person. You say, okay, well, I only need to really consider a generic person amongst those 6 and figure out what I can do. Well, let's call a line like this a friend. And if I want to say they're a stranger, I'll use a dotted line. Okay, so what can you tell me about just from this person A? How many options do I have? I've got 2 options, right? Of things that I could call B, C, D, E, and F. So what can you tell me that the pigeonhole principle tells me about all these other people? What do I know about A? She's going to be either friends or strangers with those other 5 people. And so the reason I want to think about this one is now I've got 5 people, and I'm claiming that my pigeons in this case are the people. And the pigeonholes in this case are it's the set of either being a friend or a stranger. Right? We're going to put them in one of those 2 pigeonholes. So what does that tell us? That means at least of those 5 people, what can you tell me? Well, if I call this friend and stranger, and I have 5 people, so I've got 5 things here. I need to draw, if I have 3, I've got 2 that are friends or 2 that are strangers. But actually we can draw it a little bit further and say, okay, well, at least 3 must be friends or 3 must be strangers, because I have this 5th person, right? So the most I can spread it out is 2 and 2, and then I have that 5th one. It's going to sit in the same bucket. Yeah, you have 3 friends and 3 strangers, or 3 friends and 2 strangers, or 3 strangers and 2 friends. That's the best that you can get it out there. Okay, so let's say we first have, and I'll just erase them when I'm done. If we first have this scenario where we have 3 friends, and it doesn't even matter what the other 2 are. They could all be friends, but at least we have 3 friends or 3 strangers in that mix. So is there a way that we can create this such that they're not mutual friends? Well, as soon as I draw a line between any 2, as soon as I say these 2 are friends, well, now I've got a triangle, don't I? I've got 3 mutual friends. So, I can't do that because I'm trying to avoid it. So I'm going to say they're not friends. And then if I draw a line between D and E, well, now again, I would have this triangle here. It means A, D, and E are all mutual friends. So I don't want to do that. I'm going to try to avoid this. So, but what about C and E? If I make them friends, if they're friends, now I've got 3 mutual friends. So, nope, not going to do it. But if they're not friends, that means I have 3 mutual strangers. So no matter how I handle that, I get the same result. Okay, so that's just a sketch of a fun way that you can get to various things. This can be used to solve bigger issues. And I'm going to post a link in along with today's lecture about lossless data compression. So here's the sketch of it. So if you have files of a certain size, so a certain number of bytes, what this says, and it uses the pigeonhole principle, it says if you don't want to lose information, no lossless compression algorithm, meaning you're going to reduce the file size, but you don't want to lose any information, can efficiently compress all of the possible data. So for all the possible data sets that you might want to, like you want to shrink the file size, it means there's some file that won't reduce in size. So for all the possible files, so your goal when you compress something, right, is that you make it smaller and it takes up less space. But you don't want to lose any data. So when there's an algorithm, what the pigeonhole principle says is that there is some file that won't reduce in size. So it won't get bigger necessarily, but it won't get smaller. And that's an important thing that was learned through the pigeonhole principle in computer science. Anyway,